So we got like today's application.
Okay.
So I have like the
Your radar works. So
the Dolphin bar works. We start doing pulse ranging at like 11:30.
Okay.
I'm not pulse ranging.
This is already working. So let's wait for everyone to come and we can start. 2 to 3 minutes. Still.
You look very good.
You look very good, thank you.
Where's the tie for me, man? Where's your tie?
No tie, come on.
You look very
you
good.
suit it out.
Isn't it formally enough?
I have the full suit on, yeah.
Yeah, it's pretty good.
Setting the bar high for you guys. And he's got like consulting. He needs to get the friggin' suit thing, like a tie, shoes.
The last day in academic work,
Yeah.
Andrew, last day in academic work, you can.
Signing bonus.
That's not it. But come on, you're professional. You
Yeah,
can call
yeah,
your
they-
MIT environment,
they
no
come
no doubt.
Enjoy your last day of jeans.
Oh,
Yeah.
Oh,
Douchebag.
I think you've entered the God's under.
Yeah.
Crazy. Pouring out there.
it is. Yeah. It's gonna be like that.
Wait. Yeah.
Here all day.
Oh, yeah?
so what happened with you?
Good.
I heard about the.
Yeah. Fourth time in but the person gave you second time. No, like one around town.
Great. Hi, Chichi. Can you hear me?
Yeah, I can hear you. Can you hear me?
Yes, I can hear you perfectly. Great.
Great.
Okay, so I'm waiting for a couple other members to come show up in the room, and we'll get started. Raul is also ready in Google+.
Nice. Hey, Raul.
Well, I think he's in mute, but he's here. Yeah.
Oh, okay.
Okay. So let me just let's make sure that you see the first slide.
Yes, I do see your slides.
Okay. Perfect. So we'll get started as soon as everyone else shows up.
Okay, great.
Thank you. Stand by, please. Thanks. Okay. We're all set. We're all set online. We just people. Hi. Hi, Professor. How's it going? Thanks for coming. Good. Good. Let's. I'm just waiting for Jaime and Kay, and we should be I'm the department representative, and we should be ready to start.
Who's your rep?
Sertak Karaman.
Oh, yeah, okay.
We'll have one joining.
We have Raul Rodriguez online because they are. I mean, it's a sample, so they're not around. And then the rest of you are. But let's see. I mean, they should be. Thank you. Great. Hi, how are you? Thanks for coming. So we're waiting for Jaime and we should be ready to start now.
I saw Jaime this morning. He is.
Yeah, he's, Jim told me he's here, so.
Yeah.
Okay. Sí, yo creo que sí. Thanks. Hi, Kwong. How are you doing? Good. So we're using Jaime. Yeah, have a seat over. Yeah, I have a cable connection.
Oh, you had to be for now?
Yeah, I have communication with you.
I see. So, no problem.
Okay, so let's see. We're almost ready. Yeah, I guess that's standard.
And you?
Hi. Okay, so we're just missing Rob. He just called that he's stuck on a traffic jam, so
I know, but I think we should get started.
I mean,
How
he
about
said he will
Raul?
show up as soon as possible.
Raul connect from
Yeah,
video.
Raul and Chichi are both online.
Online,
They're here.
I think we should get started in the interest of, and Rob will be showing up
Here.
perhaps now.
Almost. Almost.
Almost.
So anyway, we're going to get started. I'd like to introduce Joel. See that a lot of you know him, and you see the type of work he's been working on. Look forward to your presentation. Joel did both the master's and the PhD here in the department. His master's was in a related topic, and he is a graduate from the Polytechnic University in Barcelona, and been with us since 2009. Is that correct? Yeah. So, Joel, the floor is yours.
Thanks so much for the introduction. Welcome, everyone. Thanks for coming. And I'm going to present today the work I've been doing in the last few years here. So that's simulation and design optimization of wave propagation in heterogeneous and structured materials. So let me first start by motivating this work a little bit. We are all very familiar with how waves propagate in homogeneous media. If we have a point source like that one over there, this is a little bit how the propagation pattern of the wave looks like in a homogeneous media. However, if we consider a perturbation in the material distribution, and this would be, for instance, in electromagnetics, this would be a dielectric rod, we see that the propagation pattern is affected by this perturbation in the material. If we complicate a little bit more the scenario, we see that the propagation pattern gets more and more complicated every time. And the nice thing is that if we give some structure to this perturbation, to the material distribution, like here, for certain frequencies, we can control wave propagation. So in this case, we see that there's no wave propagation at all throughout this somehow periodic arrangement of dielectric rods. This allows for the creation of, for instance, waveguides, just by removing one row of rods. And if we keep going, we can do waveguide bands and many more things in these lines. So overall, what we want is to design material patterns that can control wave propagation. The physics behind this problem is what it's called a band gap phenomenon. And this works for both electromagnetics, but also for elasticity and acoustics. But the idea is that there's a certain range of frequencies that the propagation of which is not allowed throughout this periodic arrangement of rods in this case. But there are many more structures that one can build thanks to this band gap phenomenon. And for instance, what we see down here is a waveguide, cavity waveguide structure where just by adding a few extra rods in the waveguide, we see that for very similar frequencies that are just slightly different, one of them has a total propagation and the other one has no propagation at all, essentially. So what we see is that our structures are very sensitive to microscopic changes, and microscopic changes in the structure can have macroscopic effects, even for very, very similar frequencies. So it's a very sensitive problem as well. Overall, the main objective of this work is to develop a capability for the automated design of structured materials that can control wave propagation. And that we will do it by combining two methodologies. One of them is a numerical simulation method to be able to actually numerically represent and analyze these problems. And another one is the design optimization procedure that will allow for essentially designing different devices for the different problems. We'll do that for problems that are governed by both Helmholtz and Maxwell's equations. So in general, wave problems related to acoustics and electromagnetics. And some of the applications we'll look at is waveguides, the ones we've seen, or fibers, also frequency filters, super lenses, invisibility cloaks, and many more. So just to outline the talk, I'm going to start devising a little bit the simulation method, then we'll look at the optimization, and then we'll look at how they both combine together and how they can be applied to several applications. So let's start with the simulation method. First of all, what do we want to numerically simulate? What we want to solve here is a frequency domain problem for both the scalar and the vector wave equations. And we're going to do it in the frequency domain. It's time harmonic, so we're going to assume that the dependence on time is oscillatory and periodic, e to the I omega t, essentially. So both equations, the equations of interest will be, in the case of Helmholtz, this one above, and for Maxwell's equations, those two below. And as you see, A, B, and C here are parameters for the PDEs that depend on the materials that are present in the domain. But we want to not only simulate waves, but simulate waves in structured materials. And what do we mean by structured materials? So if omega is our computational domain, our domain of interest, we're going to discretize it in, for instance, this way. And what we're going to do is identify pixels inside our domain. So for instance, 4 pixels, D1 through D4. And these pixels can be made of different materials, but they will be constant within each pixel. So overall, the material properties A, B, and C will be piecewise constant across our domain. The main challenges for simulating these kind of problems come from the fact that we're simulating the wave equation, which is inherently an indefinite operator when we discretize it, and that has two main consequences. One is that when you go to large problems, especially in 3D, they cannot really benefit from the use of iterative solvers, and that's because the non-existence of efficient preconditioners for these particular kind of problems. But also they create dispersion errors, and therefore we want to minimize those and will require high accuracy. In particular, we solve that problem through higher order methods. Also, boundary conditions pose one of the main problems. Since as you see here, what we don't know what the wave field is going to look like around the boundary. We're truncating the domain. Ideally, it would be infinite. And what we want is that these boundary conditions do not reflect any energy back into the domain. So we'll mainly solve this problem using perfectly matched layers, as we will see later. Then we can see that geometries involve details at different scales. So if we have to capture these rods geometrically in terms of our discretization, we'll need to go very fine, and that will increase the number of degrees of freedom of the problem. Also, as we will see later, we will require a large number of simulations for optimization purposes. But there are some opportunities for exploiting and efficiently simulating these problems. And they are essentially these two. On the one hand, these problems are linear, and that's a great capability that we have to exploit. On the other hand, and this is a key feature of our methodologies, as we will see, is that there are repeated patterns. You see these rods appearing here in a structured way many, many times. So we can exploit that to reuse repeated information and save a lot of computational effort. If we look at already existing simulation alternatives, what we see is that our method mainly fixes the 3 main components that I've identified for these kind of problems. On the one hand, we are reusing information, and thanks to the fact that we are reusing all this repeated information that none of other methods do, we can actually solve in the frequency domain and with a direct solver very large 3D problems, whereas other methods need MPI implementations and the time domain equation. And also, we get scalability to be independent of the geometric complexity, because that geometric complexity is captured by the local problems, as we will see, and our global problem won't be affected. So let's already look at the method. I'm going to first look at the multi-scale CG, continuous Galerkin method, and we're going to look at this for Helmholtz equations. So Helmholtz equations, as you can see up here in the top right corner, we have both Dirichlet and Neumann boundary conditions where necessary. And what we're going to do is we're going to identify, so imagine we want to solve this problem. What we identify here is that there's a given structure on the problem. So we can see either rods or nothing. So we subdivide our domain in this case in 6 subdomains. But we see that there are only 2 classes of subdomains, the one with the rod and the one without the rod. So what we will do ultimately is only solve 2 local different problems, and then assemble that in the global sense, in these global degrees of freedom, and solve for the global degrees of freedom. This is the big picture. So we will exploit the geometric repetition through domain decomposition, and only different subdomains are solved. To get our hands on the method itself, let's first look at the approximation spaces. We are going to look at the local level. We're going to look at the standard Galerkin approximation spaces inside each subdomain. But then, independently of that, we're going to choose a global approximation space for the global degrees of freedom. And those degrees of freedom, as you see, can be modeled through a polynomial approximation order that does not need to be the same as the polynomial approximation order of the local elements. It will actually be much higher since the discretization is coarser. Good. So first of all, let me look at the local problem itself, and then we'll move and see how we assemble that in a global sense. But if we focus on one subdomain, omega 1 there, this is the weak formulation using finite element, using continuous Galerkin of a Dirichlet Helmholtz equation problem. If we knew lambda, lambda is the values of the solution field outside in the boundary. If we knew lambda, solving this problem is straightforward. The problem is that we don't know lambda. Lambda is part of the solution vector, solution field. So what we're going to do is the following. First, let me just change the notation into this one, where I call, instead of u sub h, I'm going to call it u sub f eta. And f eta stands for the forcing term f, but also the boundary condition eta. This is hopefully raw. No, I'm going to keep going. OK, so what we see is, according to this formulation, the problem above is just UH equals UF lambda, for lambda being the corresponding wave solution of the problem. Now, if we look at this notation here, we can see by linearity that U sub F eta corresponds to U sub F plus U sub eta. So we can solve different problems. This one is the one corresponding to U sub F, and we look at what this problem looks like. This problem is the forcing term F and boundary conditions homogeneous Dirichlet, so 0. We can go ahead and solve this problem for every subdomain M. We can go ahead and solve them right away and obtain U sub F. And then U sub eta corresponds to no forcing term, but Dirichlet boundary condition eta. And what is eta going to be? So eta, since we're going to express our lambdas as a span of the shape functions on the global degrees of freedom, what we're going to do is solve this problem for eta being each one of the shape functions on the global nodal basis. And what you have to note here is that the system matrix, which is the left-hand side of these equalities, are the same for all the problems here. They're exactly the same, but not the right-hand side. So once we invert this local matrix, we can then obtain the solutions by multiplying by a different right-hand side. Okay, but these are the Dirichlet problems. So how do we assemble this in the global sense? How do we couple local elements? What we're going to do is we're going to write this equation, which is the same one as before, but now I'm going to focus on the boundary nodes, on these nodes across these red boundaries at each subdomain. And what we see is that we have some fluxes left. This is a Neumann problem now. And by imposing flux continuity, we're going to get the global equation that couples all the subdomains. So this is, I'm going to skip most of the details, but essentially now that we have lambda as a span of the shape functions in the nodal global basis, we are going to end up with a discretized system that looks like this: A lambda equals F, where you obtain A and F as these dot products, scalar products. And finally, once we have lambda from this system, we just recover the solution inside by the trick we did. So since lambda is the span of the phi j's, U lambda is the span of the U phi j's by the same scalar values. So once we have U lambda, we can obtain UF lambda as UF plus U lambda, just the way we started. This is again at the local level. So this is the method. Let's look at some examples. Before I actually get my hands on into solving some of these problems, let me just give you some background on waveguide mechanisms. There are two main waveguide mechanisms. One we've already seen in the very beginning, which is a photonic crystal waveguide. In the same way, we can extend the same physical phenomenon to work at a fiber level. So this would be the cross-section of a long fiber. It's the same phenomenon. But it's more primitive, but still very efficient. It's to have a total internal reflection phenomenon, to have a waveguide. And as you see here, the way this works is essentially, because of Snell's law, if you send a wave with a high enough index of incidence, it will not transfer, and it will essentially reflect back into our material. So it will never leave the higher index material region, which you see in black. And the solutions would look like something like this for frequencies that are inside the band gap and corresponding to a high enough index. Good, so let me look first at a photonic crystal waveguide that I'm bending 90 degrees here. What you see here is the geometry we want to solve. I'm showing the perfectly matched layer. This is the PML, the region, the absorbing region that is not going to allow any reflection back into the domain. All around, especially thicker where the waveguide is pointing, and not so thick everywhere else. And what we do first here is to identify, well, we split it in subdomains. For instance, in this way. Once we have identified the different subdomains, we identify the different classes of subproblems. And in this case, we have all these domino-shaped problems, which are 4 of them, plus the homogeneous outside for the PML. And we're only going to solve these 5 local subproblems. So we're going to get the local discretizations, in this case the CG meshes. These are the numbers you see underneath correspond to the number of elements in each of these discretizations. And what you see is that if we were to solve this problem using CG, continuous galactic, directly, we would have 600,000 CG degrees of freedom. However, since we are assembling these local, we're statically condensing the local degrees of freedom into the boundaries around it, which are order 20. So inside we're using order 2 elements, but outside we're using order 20 approximation order. Remember the difference between K and P in the previous slide. So we decrease it to about 5,000 degrees of freedom. And this is the main idea. So the solution would look something like this, for instance, for a frequency which is inside the band. Obviously, we want these methods to work well, so I've checked convergence. And the 2 things I've done is, on the one hand, let me reduce the polynomial approximation order inside at the local level from 2 to 1 and compare the relative error of the transmission. Transmission is the energy that crosses a given flat boundary over here. So, and it's perfectly converged. In a similar way, what I've done is reduce the global approximation order to 15 and compare the solutions obtained with both, and it's also very well converged. So the method works as expected. And that's it. So let me move on and look at on the other type of waveguides, were total internal reflection waveguides. So this is a 3D. It's acoustics because it's modeled by Helmut. So it's 3D acoustics, total internal reflection. We have a higher index material in the green fiber that you see, and it's surrounded by air all around, and PMLs were accordingly required. I mean, I'm skipping all those details to be repetitive. We identify the different submeshes. So we have this for this side of the fiber, that for the corner, and this last element for this side of the fiber. We obviously have another one, which is the homogeneous for everywhere else. And what we see is that for different frequencies, this is the transmission pattern that we have. This is the wave propagation pattern that we have. We see that how the wave really is confined to the higher index material. So we have 2 things here. One is the confinement of the wave to the higher index material. The other one is the fact that due to the bend, some of the energy gets transferred, but some doesn't. So these are the contours plus minus 0.5 of the waves. You see how if I increase the so this is 4 times the wavelength is 4 times the radius. This is for that the corresponding frequency. Now if I increase the frequency a little bit, so decrease the wavelength, we see that we're still confined, but now the bend works worse. So there's some room for improvement in the quality of this bend, for instance. We'll look at that later in the optimization side. If I keep increasing the frequency or decreasing the wavelength, we see that some other frequencies still work well. And if I keep on increasing, we just see that as the frequency goes up, the confinement still works very well, but the behavior of the band gets more and more complicated. But that's something we would expect for higher frequencies. So this is all the way to lambda equals 1.5, the radius of the fiber. Okay, let's now move on a little bit and look at how we solve problems for Maxwell's equations instead. So if we want to focus on Maxwell's equations, I'm going to, instead of doing a multi-scale continuous alerting, I'm going to be doing a multi-scale HDG method. And the reason for that, essentially, is that, as you see here, the boundary conditions, these 2 last equations, the boundary conditions come imposed on the tangential components of the electric and magnetic fields. It's the normal times E and the normal times cross product H. So we are imposing conditions on the tangential component. Doing that in CG, it can be done, but it gets a little bit tricky in the implementation, and HDG deals with that in a very natural manner. So we're going to be doing that with HDG. So same idea, if we have this structure that we want to simulate, we identify two different types of subproblems, but now these subproblems are going to be solved using HDG. We're going to look at that in a minute. And then we will have these continuous spaces outside for the very same reason, to be able to impose these conditions in a very natural way. So let's focus on one subdomain, and let's look at how the hybridizable discontinuous logarithm, the HDG method, works for that particular subdomain. If we look at this subdomain, what we see is that the skeleton for the HDG looks a little bit like this. So we have the field components, the electric and magnetic field components. They are defined inside each subelement in the gray degrees of freedom. But then we have the traces, which are defined across the boundaries in the red degrees of freedom over there. These are the corresponding approximation spaces, as expected. The only thing you have to note is that the ones on the traces, they have this condition, this extra condition. So it's not 3 degrees of freedom. It's only 2, because you have one condition, one limiting condition to impose the tangential component. And the approximation spaces inside, they are as expected. So once we go and obtain the weak formulation of this problem with HDG for a local problem, this is what we obtain. So these are the weak equations for Maxwell's equation. Sorry. So these two first equations model the first two equations we saw in Maxwell's, and this last equation is modeling the flux continuity across interfaces for the edges that you see over here to connect and couple elements that are neighboring. We have this extra condition to remove the traces on the magnetic field. So we will end up solving only for the magnetic field, the electric field, and the traces on the electric field. Also, we have this stabilization parameter. This is just a technicality of the HDG method. I'm not going to get into detail with that. But again, some other good things about the using HDG for Maxwell's is the fact that optimal convergence has been proved in this paper by Nguyen et al. A couple of years ago. And also that the globally coupled unknowns, so the traces, the E hat, the electric field, the traces of the electric field, are the only ones we are actually solving for. Everything else can be statically condensed into those. So we only solve for E hat, and then we recover the rest of the degrees of freedom. Now the question is, how do we extend this to the multi-scale level? What we're going to look at, if you remember from the previous case, from the multi-scale CG, is that we were doing Dirichlet local problems, and then we would assemble them in a global sense through a Neumann flux continuity problem. So what we're doing here, again, is you look at the Dirichlet boundary condition that shows up here, and this is what is going to change. Now when we do multi-scale, what we see is that this is turned into lambda, which lambda is the solution that we're expecting on the global edges that you see here. But now we need an extra equation that is actually coupling subdomains with subdomains. But that extra equation is going to look very much like this one. It should, right? This one is coupling subelements at the subdomain level, and this one is going to be coupling subdomains. But it's the same physics, so it's going to look very much similar. So it looks very, very similar. The only thing is that we now may have Neumann Dirichlet conditions outside, or combination of both. So this is what's going to define the global problem. This is the flux continuity that is going to define the global problem. And if we look at it algebraically, this is a little bit what happens. We have a system of equations that depends on the electric field, the magnetic field, the traces of the electric field, and then the global variables lambda. And what we have is that these components, the A's, can be statically condensed from inside EH to the traces U hat, to the traces E hat, sorry, the traces of the electric field. And then those can be at a second level, again, raised and statically condensed into the global lambdas. And we are optimally only going to solve for lambdas and back substitute to obtain every other degree of freedom. Good. Let's look at Maxwell's equations examples. First of all, let's look at photonic crystal fiber. So this would be the cross-section of a fiber, again. And we identify different subdomains. I mean, this is just a cross-section, but I'm going to be solving the 3D problem, so we need 3D discretizations. We have two types of measures, the one corresponding with the air hole inside the higher index material, and the other one which is homogeneous. However, this homogeneous mesh is going to be used for different subdomains. And these are some of the numbers that you can get from this problem. So if it's an 11 by 11 by 35 subdomains. So overall, what we have is that using HDG, the homogeneous mesh corresponds to 78,000 degrees of freedom for the HDG problem. The one with the hole, the air hole, corresponds to almost 500,000. And if we compare that with the global problem has the corresponding phases to the number of subdomains we have. We have about 13.6 thousand phases overall of order 6. These elements were order 2, so the meshes were here and they were order 2. So overall, what we see is that the global multi-scale HDG method has about 1.3 million degrees of freedom, in contrast to if we were to use HDG directly, which would be about 700 million degrees of freedom. Obviously, these are higher orders, 6 in contrast to 2, so the matrix is a little bit denser, but it's significantly smaller. And if we now pick a frequency which is inside the bandgap of this periodically arranged structure, what we see is that there is only propagation inside this core, and this is what it looks like after the 35 subdomains, one after the other. A very similar example, but slightly different. This is a photonic crystal slab instead of a fiber. So what we see is a waveguide here that has a Y bend, a Y-shaped bend. It's a hexagonal lattice. We identify again, it's all surrounded by PML, by the way. So this is, you just see the slab, but it's all surrounded by PMLs. Then you identify 2 types of subdomains, the ones with the rod, or the hole, the air hole, sorry, and the ones without the hole. These are again some numbers. What you see is that globally, the multi-scale HDG method has about 500,000 degrees of freedom, and if we were to use directly HDG, it would have about 400 million degrees of freedom. And now I'm going to get the solutions for this problem and just cut a slice to the center line, and this is how it looks like. So this is the propagation pattern on this Y shape using Maxwell's equations. I mean, for a problem like this one, to be honest with you, it takes you longer to actually send the data from the computing machine to the plotting machine than actually solving the problem. So it's already 30 gigabytes of data. Now the big problem becomes how to deal with that more than actually solving the problem. And what I'm showing here is the time solution of this problem, but it's easy to obtain from the frequency domain since, as I said in the beginning, we just assume oscillatory periodic dependence on the time. Okay, before moving on into the optimization, let me conclude the simulation section by validating some of the results. First, I want to validate them comparing with a state-of-the-art alternative, which is this finite difference time domain developed by some colleagues here at MIT. And this is the state-of-the-art for these particular kind of problems if we look at electromagnetics. So this is how the propagation looks like for a frequency which is inside the gap. And these are the accuracy, the convergence plots. So if you look at the dashed line here, the dashed line is the convergence of the FDTD method for these choices, 5, 10, 15, and 20, of number. This is number of elements per period and direction. So if you pick one period here and one direction, this is whether we have 5, 10, 15, or 20. Using FDTD, it's the dashed line, the convergence. And the other colored lines correspond to our method using different global approximation orders. So this corresponds now to the local approximation order, again, 5, 10, 15, or 20, number of elements per direction and period. But then if we use a global approximation order of 5, what we see is the dark blue line. What we see is that for 5 and 10 local, it converges fairly well as expected, but then it gets stagnated. But that we would expect because now the accuracy of the problem is limited by the fact that globally you're only using order 5. Then if you move to order 10, you see that you go a little bit farther, but again, you get stagnated after you go 15 locally because you're limited by the global choice of polynomial order 10. And if you go to 20, obviously, then you expect the rate of accuracy that you expect. And this is only accuracy, so if on top of that you consider time, I mean, for a given accuracy, using our method is significantly faster. At least I've observed it to be significantly faster than using FTT. Okay. Also, I wanted to check that our method matches some of the experiments reported in the literature. So I went back to this paper in 2001 from Shaolin and Johnson here at MIT and others. They built a Z hexagonal lattice waveguide, and they got these results. The pink and blue points in this plot correspond to the experiments that they obtained. This is essentially the range of frequencies that are inside the bandgap for the same slab, photonic crystal slab. And I simulated the problems, and I obtained solutions that match up to the tolerance that we expected, or that they expected in the paper. So let's just pick 2 frequencies and see what happens. If you pick the 3D simulation and you carry it in you show just a slice on the point where there's essentially 100% transmission, you get 100% transmission. And if you look at what happens down here, obviously the transmission is here about 10%, and this is what the propagation pattern looks like. Okay, so just to conclude this section, let me summarize the contribution from the simulation part. First, we've developed and implemented a multi-scale CG method for Helmholtz in 2D and 3D. We've extended that for Maxwell's and just by using HDG instead for problems, especially Maxwell in 3D. And something that I've not shown in the thesis, but that I just not shown in the presentation, but you can find it in the thesis, is that we've extended the multi-scale CG for solving eigenvalue Helmholtz problems, and this is just the solution. Some of the eigenmodes of a cube in 3D, of a homogeneous cube. Okay, so let's move into the design optimization section. I guess it's appropriate that you just got here for this one, Rob. So these are the kind of problems that we're interested in solving. So we want to minimize a certain functional, J of U epsilon. U is the solution, and epsilon is the material distribution. Typically the permittivity, but it could be the conductivity depending on the problem or some other properties. We want, obviously, the PDE to be satisfied, the discretization of the PDE. So we want U to be the solution, the wave solution to that corresponding geometry, that epsilon. And we want epsilon to be binary. This is one of the main drawbacks of this, of the main challenges, not drawback, the main challenges of this problem is that this design variable is going to be binary. The first thing we can think of is what happens if we relax this binary constraint. So if we relax it into a continuous constraint, so epsilon between 0 and 1 instead of being either 0 and 1, I'm just going to show you one example where we can see in a very simple example that solutions do not generally provide discrete patterns. I mean, it could be the case, and if it is the case, then great, but in general, it's not the case. So let's look at the frequency filtering in 1D. This is a very simple problem. We have a planar wave coming from the left. We want to design a material in this design region here such that the wave that is transmitted to the right side is 0, essentially. There's no wave, so it's essentially blocked by this material. If we do the continuous relaxation and we solve this problem, I solve it using adjoints in this case, but it doesn't really matter the method. What you see is that you obviously obtain optimality, so you get no transmission at all, but you don't get feasibility in the binary sense. What you get is, if let's say air is white and silicon is black, what is gray, what is darker gray, what is lighter gray? So we don't really know. We cannot manufacture something like this. One approach is try to project this structure into the closest one. So take the darker grays and stick them to, bring them to black, and same with brighter, take them to white, and see what happens. Then obviously the solution is feasible in the binary sense, but then it's not optimal, it's suboptimal. So we lose optimality. We would love to have something like this. In this case, we are both feasible and optimal. And this is something we will get with our methods that I'm going to present just in a couple of slides. Some other challenges, that's what we were in the challenges section. So it's a PDE constraint problem. So the dimension of the constraints is very large. I mean, we may have thousands, hundreds of thousands, even millions of rows as constraints. Then it's a nonlinear and non-convex problem. So expecting global optimality is something just too naive, I would say. So we will need to be happy with good performing local optima. And as we've seen, since it's typically discrete, the complexity, the theoretical complexity is going to be in general NP hard, and that means that it's exponential in cost. In cost with respect to the design variable size, to the amount of design variables. And the set of design variables is going to be large. We're going to see that it's going to go from several hundreds to several thousand, depending on the problem. So it's going to be large. But obviously, some opportunities, some room for positivism. On the one hand, the sensitivity. So if we change the distribution of material just by a little bit, if we just change a pixel here and there, we do not expect the solutions to be randomly different. Just because this is a physical problem, this is it's PDE governed. So if we just change it at a small enough size, the solutions are not going to change arbitrarily. So this is something we're going to exploit a lot. And another one is obviously that since we cannot obtain global optima, at least we know that local optima, if they are good, they can be very helpful for the community because they can already provide insights for different applications. Comparing again with other existing alternatives for the optimization, what we see is that our method pretty much satisfies 4 of the main properties that I've identified as essential for solving this particular kind of problems. On the one hand, we are guaranteed to obtain always discrete patterns, in contrast to topology optimization, because we use discrete sensitivities. Also, we exploit the physics of the problem. As we said, this sensitivity is not being randomly, arbitrarily large. Is something we're going to exploit. And also, we can really describe very, very small features in contrast to level set methods. And more details of these you can find them in the thesis, but it's just an overview of what's out there. So let me look very quickly at the optimization method. This is a very simplistic view of it. So this part is just the local search algorithm. So imagine we are at a given state, the gray one here. So let's say we have only 3 design variables for simplicity, epsilon1, epsilon2, and epsilon3. We're at the gray state here. And we're going to compute the solution, the wave propagation pattern, at our distance 1 neighbors. In this case, the ones marked in red. Once we compute that, we can obtain the binary gradient, binary sensitivity information through these formulas here. And if there's any of those that improves our value, we're going to take it, move there, and iterate. If none of them improves, then we're done. We've converged. The problem is that this algorithm is already way too expensive. This is just a local search heuristic algorithm, but this is already way too expensive because it involves solving the simulation problem that we've seen for all the neighbors, for all the distance 1 neighbors. And distance 1 neighbors, in this case, there were only 3. But I mean, when we go to about 1,000 pixels, we're going to have 1,000 problems at each iteration. And that's already too expensive, too expensive computation. So we're going to exploit the fact that the problems are not are a little bit sensitive, but close-by configurations provide close-by solutions by using reduced basis. And what I'm going to do is, instead of computing all the neighbors exactly, what I'm going to be doing is just computing a few of them, a handful of them exactly, L of them. And with those, I will form a basis and compute approximately every other neighbor in a very, very cheap way. So then I can get an approximate for every other neighbor. And I'm going to compute the binary gradient with those approximates instead of with the original exact simulation. Then I'm going to take the candidate that improves the most, the objective function value. And for that one, I'm going to compute the full model, because I want to check that if I'm moving there, I'm actually moving to the right direction. If it actually gives me the right direction, so if it actually improves the objective function value, then I take it and I iterate. If it doesn't, because the approximation wasn't good enough, then what I'm going to do is enhance the basis with that solution so that in the next iteration it doesn't show up, reject it, and go back to compute the neighbors. So this is how we exploit the physics in the optimization sense. So let's look at a very simple problem. This is a heat equation, so you see it here, and this is the source term. And what I want to do is to minimize the norm of the solution across this square domain. Here you see that the functional is just the norm of the solution, because that's what I want to minimize. I'm subject to the PDE being satisfied, of course. And then I want epsilon, in this case, is the conductivity, to be binary. I'm going to choose either 1 or 2. But I have an extra constraint, which is a volume constraint. Because, I mean, if I'm minimizing the norm, it's like maximizing the flux in the end. So if I didn't have this volume constraint, we would just pick the conductivity to be 2 everywhere. It would go as fast as possible. So for this problem, we need this extra volume constraint controlled by beta, which is a value between 0 and 1. If I solve this problem, excuse me, this was one of the pixels is defined by these squares, which is at the same time discretized like that for the simulation. If we solve this problem using a continuous relaxation, and I obtain the solutions using adjoint methods, this is what we obtain. This is the value of the objective function value, this 0.0825 and 0.993 for 2 values of beta. And obviously, it's optimal, but it's not feasible in the binary sense. It has grades. So the first thing we can do is project into the closest one, satisfying the volume constraint. And if we project, what we see is that we increase the value of the ejecting function, so we're losing optimality, although now we are binary. And this is what people maybe was doing so far. But now if we use our method, what we see is that we are still binary, and we've improved, with respect to the projection, we've improved the value of the ejecting function. OK. So just to conclude this section, we've developed and implemented a binary gradient coordinate descent heuristic method for the design of structured materials. And we've tested that in a heat transfer problem. Also, I'm not showing it in the presentation, but in the thesis, this method has been developed as well for eigenvalue problems and in the case of Helmholtz equation. Okay, so let's get to the final, well, not the final section, but the one on applications. First, let me look at the 2D cloaking problem. So in this case, just for you to understand the problem, we have a planar wave coming from this left side, and we want to hide an object, make it invisible on this D region. So we want to do it by designing a given material on the C ring around it. And we're going to measure it just by testing the norm of the scattered field on this B region on the right-hand side. So this is the shadow behind the object. We want to take this scattered field to 0, ideally, behind it. One of the optimal patterns that I've obtained, which has decreased the objective function here, so the norm of the scattered field, it has decreased it from a factor of 99.95%. You see it's very optimal up here, and it's binary. This is the not trivial, not intuitive shape that we've obtained. Also, another optimum, I've obtained it by increasing the size of the objective region. In this case, the optimality is not as good, but it's maybe more practical because the region is just larger, and you essentially, in this case, obtain invisibility everywhere behind the object for this shape. And I'm, by the way, using epsilon 1 is the white, and the black is 3.4, which is a polyamide, which is a relatively standard material used for these particular problems in electromagnetics. Let's look at wave events. We've seen how to simulate this problem before. Now what I'm going to do is try to optimize the transmission fraction after the bend. So I'm going to remove the element on the corner. I'm going to remove it. I'm going to rediscretize it into this pixelization. It's a 20 by 20 pixelization. There's a discretization inside, of course, for the simulation. And then I'm going to, for instance, start from this initial guess and see what happens. So for this initial guess, my transmission fraction is only 78%. But then I optimize from here, and what we get is a shape like this for this specific frequency, which has risen up the optimal value of the transmission up to 99.7% for this specific frequency. So if we compare this with what people are using in the literature in a very naive way, so the first naive approach is just to bend it in the same way I did in the very beginning. And for this case, for frequencies like this one, you already get 96%, which is fairly good, but can get better. Then another option is to, instead of a 90-degree bend, put consecutively two 45-degree bends. And in this case, you can bring it up to 98%, so only 2% of losses. But then we see how we decrease it for the initial guess, but then after we optimize for this specific frequency, we can take it up to 99.7%. Let's look at the other example we looked at in the simulation section, which is the fiber. So what's the shape that I want to have here in the corner to maximize the transmission across this fiber? And very naively, what we can take is the intersection of two fibers very easily. And for this specific frequency, we have a transmission fraction of 35%. I can then try to project this into a 10 by 10 by 10 pixelization. And this is what's going to happen. So this is the projection of that into a 10 by 10 by 10 pixelization. We drop transmission, so we get down to 19%. But then I optimize from there, and we can increase it all the way to 88%, getting this shape over there for this specific frequency. The last example I'm going to look at is this photonic crystal slab. So this is the geometry we are simulating here. The white is a silicon slab, so it's permittivity 12. But then in black we have air holes. So we drill air holes, which is permittivity 1. We remove our air hole that was here, and we have a 27 by 20 pixelization instead. And we're going to measure the transmission in these B sections over there. And I'm going to solve this problem both in 2D and in 3D. So for the 2D case, these are the meshes that we identify locally. And for the 3D case, these are the meshes that we identify locally. Probably should reshuffle them. Okay. So let's look first at the 2D solutions. If we solve for the naive rod in the corner, this specific frequency gives us 87% of transmission. Now I'm going to take this rod and project it into my 27 by 20 pixelization over there. And once I project it, I get this shape, which is very similar, but with less resolution. So we lose a little bit of transmission, down to 84%. But now I take this one, which lives in my pixelization, and I can optimize from there. And we optimize from there, and I get to this funny-looking shape that increases transmission to 95%. And now let's look how this works in 3D, because this is 2D, but we want to actually ideally build a slab, so we want to see how this works in 3D. So I'm going to take the naive rod again, and this is the propagation pattern in 3D. Now in 3D, I only have 32% transmission, because in 3D we have losses on the Z direction, on the third component of directions. Then I project that rod into my pixelization. You see here the resolution we have. And it drops down to 25%. And now I use the optimization in 2D. So this is not the 3D optimization. This is the optimization in 3D. I extend it in the third component. And what we can get is 61% transmission for this specific frequency. And this is a 3D slab. So this is actually, if we had the materials and the capabilities, we could go and build specifically this geometry. Okay, so let me conclude with a summary of contributions. We've developed, first of all, a simulation method using multi-scale methods for Helmholtz and Maxwell's, for the source problem and for the eigenvalue problem, and both in 2D and 3D. We've also developed and implemented a binary optimization method for the design of structured materials. And we've done all that by comparing with the state-of-the-art alternatives and checking convergence and all that of our methods. And finally, we've demonstrated the validity of this new paradigm for design with several examples involving either cloaking or waveguides. As for future work, we have obviously the two fronts, the simulation and optimization. For the simulation, I mean, it would be great to include high order and coarse meshes to especially decrease the degrees of freedom in the local problem. That would help to decrease it. I mean, the global problem is the one that is going to be limiting anyway. But if we can decrease, if we can do better in the locals, it's also good. Then we could consider and think about doing a nested multiscale. So you saw, for instance, in the 2D photonic crystal bands, I used 3x3 subdomains. I could have maybe 1x1 and then 3x3, so several levels of multiscales. And also extend to the eigenvalue equation for the ATG Maxwells. As for optimization, we could take into account further manufacturability constraints. For instance, we wouldn't like to have pixels of a given material surrounded by pixels of another material, but that's still very complicated to manufacture. And we'd love to have robust solutions so that then when we go and actually manufacture those, we can rely on having some tolerances over there. But also with respect to the frequency, because then we would have solutions that are valid for a given range of frequencies. So we would love to have robustness both with respect to the structure, but also with frequency. And we could also consider pixel adaptivity to get as fine as we want it, ideally. I don't want to conclude before acknowledging everyone that has helped me so far. On the one hand, my advisors, Jaime and Kay, it's been great to work with them all this time. Also my committee members and readers, extended to my research group, my mentors who helped me get to MIT, the rest of ACDL, my friends here, but also there, and my family and Christine, of course. Obviously, the financial support is quite important as well. And that's it. Thank you very much.
Any questions?
Yeah, I can. Could you on the wideband that you do both in 2D and in 3 dimensions? When you saw it in 3 dimensions, you say that you have PML on both sides, so it's really absorbing conditions top and bottom.
Yes.
So that okay, it's not surprising. So there is no confinement at all. You don't even try to do index hiding in the vertical direction.
It's not required for a problem like. It's not required for.
When you are high.
Yeah, let me actually show.
Okay,
let me show it here. It's not required here because somehow you have total internal reflection in the slab.
Already, because it's higher. The green is the higher.
Exactly. Another story is.
It was rotted with the.
Is an example like this one on top left.
Now you need to have.
In this case, you need to have
guiding in the
exactly. Yeah, that's a good question. But for the photonic crystal slab with hexagonal, where the material is the slab and there are holes, in that case you don't need to have anything in the third dimension. Yeah, but in this case, to get something like this, you definitely need to confine it in the z direction. Otherwise, it would scale. Yes. I don't know if.
So I have a question.
Yeah.
Could you go to the discretization part? You have shown like the discretized like 3x3 elements right, in your like, waveguide scenario.
Yes. So.
Right, that's probably like the second part of representation. Yeah, you could use this. Right.
Hmm.
So First of all, why 3 by 3? Is this an arbitrary selection or is this?
So this is a very, very good question. Actually, I've tried this problem with 1 by 1, with 2 by 2, with 3 by 3. It turns out that in terms of computational cost, it ends up being the best, 3 by 3, but it depends in 2D and 3D on the problem. The idea here is that if you want to do the local problem as big as possible to reduce the global problem, but you do not want to do it too big, such that it's more expensive than the global. So in this case, since the meshes look like this, ideally this one takes as long as the global. It's about a few seconds, the same amount of seconds. It's not the order of seconds. So it takes very similar time. So that's what you want ideally, that both problems take the same time. Because if the local takes more, then the global takes less, but you are spending a lot of time here. If it's the other way around, then the local is too small. Another thing is that for this configuration, having 3 by 3 is not a big problem, because I only have 1, 2, 3, 4 combinations of these 9. But if I had here a weird shape where I could have 2 to the 9 combinations of these rods, then I would need 512 local elements, which it would require to solve 512 different local elements, and you're not exploiting as much this multi-scale. So it's really a problem-dependent decision, and it's something that whoever chooses this has to choose. You could always do 1 by 1, but if you want to get the most of the method, in this case, for instance, you should go to 3 by 3.
Again, just a random thought. Would that matter if you cut, for example, your domains into half of their cylinder, so that you can increase some kind of symmetry, or you can benefit from symmetry?
Yes, of course. In problems like this, you could exploit symmetry. First, you could exploit it on the local element level. I mean, this one and that one, you don't need to solve 2 of those. You can solve just one and then rotate it. But then also if you look at here, I mean, you should have some symmetries that you could exploit, for sure. Somehow the idea of this source problem solution is to show how you can go and solve in one shot the entire domain without using symmetries. But obviously, if you can use symmetries, why shouldn't you? Absolutely, yeah, I agree with that. Yes. I don't know if...
Make sure they are still there.
Yeah, I hope.
So do you look at how you automatically identify the subdomain in terms of computational cost, or a given problem?
I haven't done that analysis doing the math, but it could definitely be done, because you can count the degrees of freedom.
This kind of this gives you some like adaptivity.
Exactly.
You automatically identify the substructure that you don't have to let the user.
I totally agree with you. We could have a quick count of orders, degrees of freedom, because it depends not only on the discretization you choose, how fine it is. It also depends on the polynomial order you choose, because it's all about the cost of the local and the cost of the global. So we would definitely develop. Give me the polynomial order you want to choose, the discretization you want to choose. I'm going to compute the cost of solving that local system. I'm going to compute the cost of the global, and I'm going to compare whether 1, 2, or 3 by 3 work better or worse. I totally agree with you. That could have been done, and that's something actually to think for future work, of course. Yeah. So let's see if either Chichi or Raul have questions. Are you there?
Yes, I'm there.
Okay.
Can you hear me?
Yeah, I can hear you, Chichi. Please go.
There too.
He was on mute, but I hope he's there.
Raul?
He's here. He's here. Okay. So let's go first with Professor Wang. Please.
Okay, I have a question about the coordinate descent method you are using to optimize do optimization. So,
yeah.
So your formulation of the gradient or derivative is very interesting. You are taking a finite step instead of an infinitesimal step in the definition of the derivatives. But in some sense, you are taking any infinitesimal pixel in your simulation, not infinitesimal, but like a very small pixel in your simulation. Can you derive a theory that is similar to like the normal gradient as the size of the pixel goes?
That's a very, very interesting question. I mean, there's a full discussion about that on the thesis, because it's a very interesting point. I mean, we are doing finite steps in terms of the distance we move, but the size of the pixels could be arbitrarily small. And there's a whole theory of topological gradient, it's called, that there's a whole theory that essentially proves that if you can essentially go as fine as you want in terms of the pixel size, you can derive the same ideas that you have in the classical gradient definition. So it's a great question, and it's a great point that you arise. So the answer is yes. If you can go arbitrarily small in the size of pixels, there's a full theory that proves that the existence of a negative value for this gradient only if there's a possibility of improvement is warranted, which is what the continuous gradient says essentially. The problem is that you can never go arbitrarily fine, so you have to choose a resolution, let's say. And in my case, I would say the resolution for most of the problems is not small enough to capture the fact that I could guarantee that they are global optima. So I'm not in the situation of saying my optima are global, because I think if we refine them further, we could still probably improve that. But yeah, it's a great point, and I mean, if you're interested, I can send you a couple of papers on that. It's called topological gradient, and it's essentially a parallel way of defining gradients for topological problems like this one.
Okay, thank you.
Yeah. Raul?
Well, first of all, I really enjoyed the presentation.
Thanks.
It was very clear and entertaining, and also informative. I actually have two minor questions that I put it on the chat window. When you compare with the FTD method, I forget what slide that was.
This one, right?
I seem to, some inversion of the colors there. You see that you have the red and the blue are inverted.
Well, the red is 15.
No, keep looking at the content.
Oh, here, yeah. I agree with you. The +1 and the -1 that uses FTD and that I use are opposite. Yes.
Okay. All right. Just want to
Yes.
make sure.
Yes. You can see.
And then to go to when you made all the statements about the continuous method for optimization. Are those schematics, or are those actual simulations that you run? And
you mean this one?
Yeah, that one and that one.
And
the very next
yeah, so these are actual computations, yes.
actual computation.
Yes, this is a problem. I've obtained the top one using adjoint methods, and then I projected it to the closest value, and then that one I've obtained using my methodology, yes. And the same thing for the heat problem.
Very good.
So the same thing here. The same thing here.
Yeah. Okay. Thank you.
All right, thanks. I don't know if there's anything else. Thank you. Okay.